In supervised learning, life is simpler. We have a dataset of our inputs, here written as the axis, and our labels y. So the input of our model is the vector of all features. We can then learn a parameterized function f theta of x, where theta are the learnable parameters that predict the labels based on the input, here written as y hat. I have recorded another video of a complete introduction into neural networks if you are unfamiliar with this. But overall, we need to find the parameters of our model that minimize the expectation of some loss L based on samples of the dataset. To do so, we can, for example, use a gradient descent algorithm, which updates the parameters based on the gradient of the loss. But what if we don't know what the optimal labels are? For example, what if we need to predict how the robot should move to solve a certain task? We don't know these movements, also called actions, as they act on the robot. Rather, we can try out some actions and get feedback in how good these predictions were according to a task. So we still have a function taking in the input A, but we only receive a feedback. This is a separate field in machine learning called reinforcement learning, and in this video sequence I will explain all important concepts of it. But first, let's understand reinforcement learning on a higher level. Okay, so if we don't have the labels or actions, let's look a bit closer into what the exact setup for reinforcement learning is. We have a model, let's call it pi, with learnable parameters theta. It receives an input, let's call it S for state, and I will explain later why we call it state, but for now let's just look at it as some input we received from a dataset, as it is most commonly done in classic deep learning tasks. This model then outputs a prediction A, which stands for action. So far, this is very similar to the supervised learning task. Based on some input S, the model outputs a prediction A. However, we don't know what the true label A is. Thus, we cannot compute a loss in minimizing the difference of the prediction to the true value. So our computation continues. This predicted action is fed into a system that we do not control. So for now, this is a black box. The black box somehow evaluates the action in the context of the input S and returns a scalar feedback signal R. We call this feedback the reward, as it rewards good predictions and penalizes bad ones. Again, we do not know how R is computed. We can only observe its output. The natural objective now becomes in predicting the most accurate actions that would solve the task. To quantitatively express this, we want to choose actions that produce the maximum reward. So we want to adjust the parameters theta of our action prediction model such that the reward produced by the actions through the black box becomes as large as possible. At first glance, this looks similar to supervised learning. Instead of minimizing a loss, we maximize a reward. So we could just minimize the negative reward by computing the gradient of the reward with respect to the model's parameters. So let's try this. If the reward were a known differentiable function of the action, and the action was differentiable with respect to the parameters, we could apply the chain rule. The gradient of the reward with respect to the parameters is the partial derivative of the reward with respect to the action times the partial derivative of the action with respect to the parameters. That just means we derive the function that yields the reward with respect to the action, and we derive the function that yields the action with respect to the parameters theta. The function computing the action is simply our model, which is typically a neural network and therefore differentiable. Therefore, we can compute the derivative of A with respect to the parameters. The problem, however, lies in the first derivative. The reward is produced by a black box model. We do not know its internal structure or whether it is even differentiable. In most real-world problems, it is not accessible to us. Thus, we cannot differentiate the black box and cannot compute the gradient. This is the key conceptual problem in reinforcement learning. There is no gradient path through this black box, and moreover, it is not under our control. It is rather an external system we have only access to by sending in actions. We call this black box the environment. As we will later see, we can only interact with it, and it expresses what is going on in our system. Because of this gradient problem, classical gradient-based optimization cannot be applied in the reinforcement learning setup, and alternative strategies to optimize behavior purely from observed feedback are needed. To derive at these algorithms, like PPO or soft actor critic, one needs to make assumptions about the environment and exploit the sequential nature of the setup. So what is the sequential nature in reinforcement learning? Here our learned model does not only make one single prediction A. Rather, the prediction interacts with the environment, returning not only a signal of goodness, but also another input S. This input can then be passed into our model again, building up a sequence. So one can see the input S of our model as the current state the environment is in. For example, how exactly the robot is positioned in our world when learning robot movement, or the current stock prices if we want to train a trading bot. Then, based on this information, the model outputs the action A, basically changes to our environment. For example, how the robot should be moved or what stock should be bought or sold. And then this action is passed into the environment again, which changes it internally and outputs another state S. Based on this state, it also returns the reward R, indicating how good the current state of the environment is. In order to label the sequence, one usually associates a time step with every element. For example, at time step t, the model pi theta receives an input st. It then predicts an action at, which is passed into the environment that yields a reward rt, and the next state st plus 1. The full interaction can be therefore written as a sequence called a trajectory through the environment. One such trajectory, which terminates, is called an episode. We can have multiple different trajectories or multiple episodes of a sequence. Thus, data in reinforcement learning is not independent. Each action influences future states, each state influences future rewards, and future rewards depend on earlier decisions. This is what makes reinforcement learning a sequential decision problem. To reason about this sequence mathematically, we describe it in probabilistic terms. This approach will then help us later to optimize the reward. We assume that the environment transitions from one state to another according to certain probabilities. In other words, given a current state S0 and an action A0, the next state is not necessarily deterministic, but maybe stochastic. Thus, we can use a probabilistic model to describe the environment. For example, in 80% of the cases we choose this action in state 0, we end up in state 1. And in 20% of the cases, we end up in state 2. Formally, we can write the sampling of the next state from the probability distribution over all possible next states as this, where the next state is drawn from a conditional probability distribution that depends only on the current state and the current action. Before incorporating actions explicitly, let us first look at a simpler setup, the so-called Markov chain. A Markov chain is the simplest probabilistic model of state transitions. It consists of a final set of states S and transition probabilities P. Additionally, we define the probability distribution of starting states, the so-called initial state distribution, as rho 0. So we can mathematically define a Markov chain as the tuple S, P, rho 0. This model is often used to describe the change of our environment, as it makes one crucial assumption, which simplifies our model significantly, the Markov assumption. It states that the next step only depends on the present and not on the past. Thus, we can simplify the conditional probability distribution, depending on all past states, to only depend on the current state. Instead of modeling the entire past, we only need to model local transitions. This assumption is major in reinforcement learning as it simplifies the distribution significantly. Now, all of this was theoretical, but let's look into a concrete example of a Markov chain. Consider a very simple system with 3 states, A, B, and C. We can visualize this by creating a circle for every state in the environment. During any time, the environment must be in one of these states. For example, if we model the weather, we can say A is sunny, B is cloudy, and C is rainy. At any point in time, the weather is one of these 3 states. Suppose that the transition probabilities are defined as follows. For example, the probability that the environment is going to go to state B, given that it is currently in state A, is 60%. Meaning, if it is sunny, 60% of the time the weather will be cloudy afterwards. We can visualize this transition given an arrow from state A to B, with probability 60%. We can then draw the rest of the transitions and have created a Markov chain. All unspecified transitions have a probability of 0. The initial state distribution here is defined, such that the weather always starts out sunny. But why do we need this Markov chain? What can we do now? For example, this definition lets us compute the probability of observing a sequence. For example, what is the probability that the weather is first sunny, then cloudy, then sunny again, and then finally rainy? We can describe it with the following sequence: A, B, A, C. Using the Markov property, we can factorize the join probability. It is the probability of starting in state A, then transitioning to state B, then transitioning back to state A, and then finally transitioning to state C. We have defined all of these probabilities on the left and can therefore compute that the probability of observing such a sequence is 24%. The important observation is that the join probability decomposes into local transition probabilities. Without the Markov assumption, we would need to model the probability of the entire sequence directly, which quickly becomes intractable. Markov chains therefore provide a mathematical foundation in describing sequential stochastic systems and are common in reinforcement learning. But so far, our Markov chain only described how the system moves between states. However, in reinforcement learning, we are not only interested in how the environment evolves, we are also interested in how good certain states are to find suitable behavior to solve a task. To measure how good a state is, we can introduce the rewards to our Markov chain. This is then called a Markov reward process, or MRP. Suppose that whenever the system enters state C, it receives a reward of +1, as we want to stay in this state. And in all other states, the reward is 0. In our example before, let's say we have a garden and want to move to an area where it rains a lot. Formally, we define a reward function as a mapping from our state space to a scalar number. And for our example, the reward of being in state A is 0, the reward of being in state B is 0, and the reward of being in state C is 1. Now the system does not only generate a sequence of states, so A, B, A, C, but also a sequence of rewards, 0, 0, 0, 1. An MRP can therefore be defined by the tuple S, P, R, gamma, and rho 0, where S is again the state space, P is the transition probability, so the joint probability of going to state ST plus 1 when being in state ST. R of S is the newly introduced reward function that, based on the state, computes the reward. Gamma, which is somewhere between 0 and 1, is the so-called discount factor, and we will discuss this in a second. And finally, rho 0 is again the initial state distribution. While for describing state changes, we only looked into single transitions. When, however, valuing states in how promising they are with respect to the reward, we are interested in long-term rewards. So that is the total reward we might receive in the future from this state on. We therefore define the return, sometimes written as a capital R or G, as the sum of all future rewards starting at time t. We then add a so-called discount factor, gamma, to this sum, creating the discounted sum of future rewards. To understand gamma, we can visualize a sequence of rewards over time. On the x-axis, we can see all future time steps through the environment, and on the y-axis, the value of the reward after being discounted. This value indicates the actual value contributed to the total sum of rewards. To show the effect of gamma, we keep the reward during every step equal to 1. So no matter what the transition is, the reward will always be 1. If gamma is 1, then all future rewards are weighted equally, meaning if we achieve the reward now or far in the future, does not make a difference for the return. This is especially important if one has a very complex task and the reward is only achieved far in the future. If gamma gets closer to 0, however, the influence of future rewards in our current return gets lower. We tell the model that it is better to get rewards fast than some time in the future. This hyperparameter is usually somewhere between 0.995 and 0.9. As our transitions are stochastic, these rewards, even when starting from the same state, can differ. The expected return, or sum of all discounted rewards, of an episode starting from one specific state is the so-called value of that state. It indicates how good it is to be in this particular state. It is defined by the value function, which is the expected return of that state S. Or phrased differently, starting from state S, what discounted sum of reward can I expect? this already shows an important idea. Some states are more valuable than others because they lead to higher long-term rewards. However, we are still missing one crucial component. So far, the system evolves randomly, according to fixed transition probabilities. There are no decisions. In reinforcement learning, however, the agent actively influences transitions. To model this, we must extend the Markov reward process by introducing actions, creating a Markov decision process, or MDP. The key difference to the Markov reward process is the introduction of an action space A. Additionally, the transition probabilities become also dependent on the actions we choose. So the probability of going to the next state S prime depends on the current state S and action A. This means that the next state is sampled from a distribution that depends on both the current state and the action taken. Let us extend our previous example. We introduce the decision from the policy, indicating that, for example, in state A, 90% of the time we choose the action A1, and 10% of the time we choose action A2. For the other states, the policy always chooses A1. As said, our transition dynamics now depend on both the state and the action. For simplicity, we made the environment deterministic, meaning 100% of the time we choose one action, we will arrive at the fixed state. In theory, however, there could be multiple probabilities as well. Now, the agent can actively decide whether it prefers a more risky transition, A1, and end up not receiving a reward, or directly move towards C. The environment no longer evolves purely randomly. Its behavior depends on the agent's decision. With this, the overall goal of reinforcement learning is also clear. We want to learn an optimal behavior, optimal action A, based on the MDP. For this, we need to learn a good decision module that contains this behavior. This decision module, called policy or PI, describes how the agent chooses actions. A policy defines either concrete actions or a distribution over actions given a state. Meaning, in state A, it always outputs A2. This can be implemented via a lookup table containing all states. However, if the number of states becomes very large or the actions become continuous, this implementation is not feasible. One can then implement a policy via a probability distribution. Here, typically Gaussians are used to sample actions depending on the state. The parameters of the distribution can be learned via neural networks. And with that, the full inference loop in reinforcement learning becomes the following. On the bottom, I keep track of the trajectory that we have sampled so far. We first observe the initial state from our initial state distribution, rho 0. Let's say we sample S0. We then use the state to query our policy that, based on the state, outputs an action. This action is then passed into our environment, or MDP, which is currently in the state S0. It evaluates the current state through the reward signal R0. Based on the action A0, the internal state of the environment changes to S1, which is also returned. The next state is then inserted into our policy again, resulting in the next action A1. We can again apply this action in our environment, transitioning to state S2 and receiving the reward R1. This is called stepping through the environment and is continued until the end of the episode. In practice, the end is defined if the task is solved or the time ran out. We can also include the policy into our objective. We want to find the parameters that result in a policy which expected discounted sum of rewards is maximum. Again, the expectation is chosen as we can have stochasticity in our policy and transition dynamics, both shown before. And the expectation is taken over all possible trajectories included by the policy and the transition probabilities. In order to find a policy which maximizes this objective, we need to first find a measure that evaluates how good a policy is. We can then use this measure to maximize it and find a better policy. One function used to evaluate policies is again the value function. We define it under a policy pi that is used to generate the trajectories through the environment. This tells us how good it is to start in state S and follow policy pi thereafter. In other words, what is the expected discounted sum of rewards if I follow the actions from the policy pi for one episode, starting from state S? Thus, if we have two policies, pi and pi prime, we can define a better one, or larger one, being the one having a larger value function. We can also define an additional function, the action value function or Q function. This tells us how good it is to take action A in state S and then follow policy pi. So basically, what is the expected discounted sum of rewards if I chose action A in state S and then in the next state, st+1, till the end of the episode, follow the actions from policy pi. These value functions are central objects in reinforcement learning. We will later see that learning these functions can help us compare different policies and optimize them. But for now, just acknowledge that they exist. Now that we have defined value functions, the natural next question is, given a fixed policy pi, how can we compute its value function v pi of s? To make this concrete, let us consider a simple 4x4 grid world. Each cell in the grid represents a state. So we have state 1 to state 16. The agents can move up, down, left, or right, creating a 4-dimensional action space. If it tries to move outside the grid, it stays in the same cell. Suppose the bottom right corner is a terminal state with reward +1. All other transitions yield reward 0. So we can imagine that the bottom right corner contains some sort of treasure, and from every single position, we want to reach it. Since the environment is small, we do not need neural networks. We can explicitly represent the value function as a table with 16 entries, one value per state. For a fixed policy pi, the value function satisfies this recursive equation. This is called the Bellman expectation equation and looks scarier than it is. It tells us that the value of a state equals to the immediate reward, aka the reward we get from this step, plus the discounted value of the next state given by our value function, and then averaged over all actions and transitions. This average is weighted by the probability of taking this action in state S, given the policy, as this module tells us what actions we should take, and reaching the next state S prime, given the transition dynamics, as the transition dynamics tell us how likely it is to reach S prime. So in essence, weighted by how likely this action is and how likely the transition is. However, we don't know the value function. So in practice, we have to compute v pi iteratively, and this is how we can do it. We initialize all state values to 0. So v0 of s is equal to 0. Then we repeatedly update our value function by its definition. In the first update step, our value function from the next state is 0. The reward of all states except the one at the bottom is 0 as well. That's why the value function of all states not reaching the bottom right remains 0. However, the cell above and below can reach the bottom cell when choosing 1 out of 4 possible actions. Thus, their value increases to 0.25. We can continue a second iteration with the updated value function. The second iteration accounts for 2 steps, and so on. So we can continue these iterations until convergence, here shown for 50 iterations. For every iteration, we choose all 4 values of the states that are reachable. We take the discounted value and we average them. In the grid world, this means, for each cell, we look at the neighboring cells, take the current value estimates, discount them, average them according to the policy, and update the table. After enough iterations, the value converges and the value function is found. This process is called policy evaluation. It is an iterative algorithm that results in the computation of the value function of the policy we are following. I'm a big fan of pseudocode, as it clearly structures the algorithm. So for policy iteration, it would be like this. We have the policy that we want to evaluate and our environment, which is described as the MDP. We also define a convergence condition, theta. This variable defines the target difference we want the largest difference between 2 steps to be. For example, if we compute the next iteration of our value function and compare the difference of each state to the prior value function, we choose the largest difference in this step. If the largest difference is smaller than our target difference, then we stop the algorithm. Inside this iteration, we always need to update every state. We first save the old value function to later compare the new one to it, and then compute the new value function based on our update rule. Afterwards, we store the difference of the value function of that state if it is larger than any difference seen so far in this step. Finally, we return the converged value function. However, policy evaluation only computes the value of a fixed policy. Our goal is not just to evaluate a policy, but we want to improve it. For this, we can use another algorithm called policy iteration. It alternates between two steps. First, it follows policy evaluation to compute the value function under pi for the current policy. We can then encapsulate this code in a function call as we just talked about it. It then uses policy improvement by choosing for each state those actions that maximize the expected return based on the just learned value function. So the next policy follows actions of every state that based on the value functions of the old policy maximizes the return. This is achieved as we compute the return for all states and always choose actions that maximize the sum. This is essentially what the argmax says. We can then iterate policy evaluation and policy improvement to improve the policy step by step. When converged, this algorithm returns the so-called optimal policy. It is the policy that for this Markov decision process returns the largest value function or the highest return and is commonly written as pi star. In the grid world, one optimal policy could look like this. For each cell, we look at the neighboring cells and choose the action that leads to the highest value. So the arrows in each cell now point towards the most promising neighbor. We can follow it from every state to arrive at the bottom right. Policy iteration is a very intuitive algorithm. Evaluate a policy, then improve it, and repeat. However, it has one major drawback. In policy iteration, the policy evaluation step needs to be run until convergence to compute the true value function under the current policy. This can require many iterations, especially in larger state spaces, and it becomes computationally expensive. So the question is, do we really need to fully evaluate the policy before improving it? The key idea behind value iteration, the final algorithm in this video, is that we can combine policy evaluation and policy improvement into a single update rule. The difference to this algorithm is best described by first writing out policy iteration. So here's the known pseudocode. For the policy evaluation, we can remove the iterative loop as we only do a single update. Instead of computing the value function exactly and then improving the policy, we directly update the value function towards optimality by taking the best action at every state. Mathematically, this means instead of summing over all possible actions and weighting them based on the policy, we choose the action that maximizes the return. This new update rule is called the Bellman optimality update. So rather than asking, what is the expected return if I follow my current policy, we now ask, what is the best return I can get if I choose the best action in this state? This means the value iteration implicitly performs policy improvement every single update step. But why does this work? We can interpret this algorithm as follows. At iteration k, we have some guess of our value function vk of s. We then perform one optimal Bellman backup step, which pushes the value closer to the optimal value function v star of s. By repeatedly applying this update, the value function converges to v star. Then, once we have the optimal value function, we can extract the optimal policy by choosing the best action according to our optimal value function. So value iteration directly solves the control problem. Let us connect this algorithm back to our 4x4 grid world. As before, each cell is one state, so the value function can be represented as a table with 16 values. We initialize all values to 0. Now we repeatedly apply the Bellman optimality update for every grid cell. Since the bottom right state is terminal and provides reward +1, the reward starts to influence its neighboring states. In the first iteration, only states that can reach the goal in one step receive a non-zero value. This is similar to policy iteration, but notice how the value is now 0.9 instead of 0.25. That is because we only choose the action reaching the bottom right cell. All other possibilities are ignored. In the second iteration, states that can reach the goal in 2 steps receive a non-zero value, and so on. So you can think of value iteration as backpropagating information backwards from the goal state through the grid. Over time, the value table fills up and encodes which states are close to the goal and which are far away, always under the assumption that we can act optimally from now on. Once the value function converged, notably faster than the policy iteration, we can, similarly to policy iteration, create an optimal policy by choosing states with the highest value. And that's it. I hope in this video you learned the basic setup of reinforcement learning, like policy, environment, value function, and the interactions, why it is necessary, right? Because we cannot update the gradient through the environment, and how we can define a Markov decision process to help us find policies that yield task-solving behavior. These tasks are by no means comparable to complex real-world scenarios that need more advanced methods like PPO or soft actor critic. But even these algorithms build upon these fundamental concepts. In future videos, I will take you on the journey through reinforcement learning, covering topics such as temporal difference learning, SASA, importance sampling, Q-learning, and finally soft actor critic and PPO. Thanks for watching.